Today's speaker is Natalie LeBaron, and she is a second-year grad student in the astronomy department, and she'll be giving you a talk about the life and death of stars and tell you kind of where the elements are from.
All right, thanks everyone for coming. So full context, I am a somewhat last minute fill-in since our speaker for this month canceled less than a week ago. So I apologize if this talk is a little bit not as well practiced as it could have been, but I do invite questions throughout. This is mostly on my research and on my interests in astronomy. So I guess it's more, my interests specifically are more focused on the death of stars, but very interested in nucleosynthesis or how elements form and where that happens. And that also involves a lot of life of stars. So in any case, feel free to interrupt and ask questions. And yeah, let's get started. So if I can get this actually, there we go. So there are a lot of elements around us that make up us, make up the Earth, make up our solar system. Question, I guess that I'm interested in especially is where a lot of these elements form astrophysically and somewhat how they get here, how they form, and well, how their abundances tell us about the history of the universe and what kinds of physics can be going on there. So this slide kind of gives away my entire talk. Very concise graphic, but what I want to go through is basically what all of these colors and types of formation phenomena are, and where the field is maybe kind of going in the future, or what we think might also be added to this periodic table in the future. This periodic table as it is would have been completely different if I was giving this talk 10 years ago. We discovered a number of things on this graph, even within the past decade. So it's very exciting to be able to talk about it and talk more specifically about how, especially some of the more rare phenomena on this diagram work. But in any case, we should start with basics. So again, this is what our sun looks like. In terms of the elements that make it up. You can see a few things from this graph. So on this side is solar abundance. This is normalized to silicon having about 1 million atoms. So if you have about 1 million atoms of silicon, which falls right here, then you can see the lot more hydrogen and helium atoms and a lot fewer of these other heavier elements, and also these weird little elements that are not very massive, that we also don't have many of in our universe, and more specifically in our sun. So yeah. So something you might ask is, well, what determines these abundances? And well, what physics is behind that? So maybe we'll back it up even a little bit more and ask, what is an atom? So an atom is basically just some number of positively charged protons in the nucleus. And if you want it to be a neutral atom, then you add in some negatively charged electrons to orbit the atom. It doesn't exactly work like the traditional orbit. Like this isn't like a planet orbiting a star exactly, but is a useful way of thinking about it to first order. But the point is we have some positively charged things in the center and some negatively charged things that combine together. So opposites attract, right? So these positively charged protons like it when there are negatively charged electrons around them. And what really determines what type of elements is the number of protons in the nucleus. So for example, I can add things like neutrons. So neutrons are neutrally charged. They can just exist there. They don't really do anything to the atom other than add mass to it. And as you can see, even though I added a neutron, I can add 2 neutrons or more. Might not be stable at that point, but I could. It would still be hydrogen just because there is 1 proton in the center. If I add another proton and maybe another neutron for good measure, I get a new type of element, helium. And I can continue to do this. I can continue adding protons in, and I will get bigger and bigger elements. Again, if I want it to be neutral, I'll add another electron here. But you know, an atom doesn't need to have electrons to be its own element. I can take away an electron and I get what's called an ion. So this thing is no longer neutrally charged. It is now 1 + 1 positively charged because it has 2 positive things and 1 negative thing. So that it still maintains its helium nature, but now it just has an opening for another negatively charged thing to come along. Yes.
Are there any of these?
Oh, yeah.
Do you point to anything or?
I mean, they exist all around us, right? So most of the atoms in this room are neutral, but if you rub your hair or your clothes, you will ionize some of those atoms that are, you know, on you, and that creates static electricity. So we do interact with ions every day. Electrons are what is electricity in the walls.
I might have it.
Oh yeah.
Something might fall off and I'll leave them here.
Oh yeah, yeah. So like 1% of the air in this room is ions, but we're in a fairly cool environment, temperature-wise. So it's most of the atoms around us are going to be fairly neutral, and in fact, it's cold enough that a lot can form into molecules. If you add too much energy to any one of these electrons, it can actually just fly off and become. It won't blow up exactly, but it's fairly easy to ionize an atom. It's a bit harder to deal with anything inside of here because those protons, you know, you might think that these 2 positively charged things don't like being so close to each other. That is nominally true, but what happens when you get protons too close together is they start being held together by something called the strong force. So that's is a little bit stronger than their electromagnetic repulsion. So you actually get a stable nucleus. And we'll talk about that a little bit later when we talk more about forming even bigger nuclei. Any other questions?
I guess, but the only way to really do that is provide a lot of energy. You can't just throw a neutron in there. You got to force it in.
Yes, yes.
Yeah,
That is the bulk of my talk.
Okay.
I got a question.
Right? Yeah.
So in your first slide of the table of elements, it said that hydrogen is from the Big Bang
Yes,
fusion.
we're getting
but
to that.
1 proton.
Yes.
I thought fusion is when you put protons together.
We'll talk about that in a second.
All right.
But yes, so yeah, let's come back to, as you said, our very simple nucleus here. So this is only 1 proton. That is our simplest type of element, simplest atom. And as you said, these atoms are formed basically by the Big Bang. So Big Bang happened, a lot of energy and well, small but quickly expanding space. Way up at the close to the Big Bang in time. So less than about microsecond after the Big Bang, all you really had was this particle soup. And it took a while for a lot of the energy in this particle soup of mostly, well, not even protons at this point, to cool off enough for these constituent particles called quarks. So 3 quarks make up a proton or make up a neutron. It took a while for those quarks to cool off enough that they could coalesce into what we call protons and neutrons. It took even longer for the ambient temperature of our universe to get cool enough for neutral atoms to be formed, for those protons to form together, or to form neutral atoms by collecting an electron that stays bound to that nucleus. So around here at about 400,000 years after the Big Bang, so that's a big jump from about a microsecond to 4,000 years, finally did we get neutral atoms. And in addition, the universe cooled off enough that became transparent. So at this epoch of what we call recombination, which is sort of a misnomer, but it's essentially when electrons started to get bound into nuclei, that's as far as we can see back into the early universe. We get something called the cosmic microwave background from that point in time. So it's basically the remnant radiation of the Big Bang, or as close as we can get to the Big Bang. And if you have ever seen TV static, some small percent of that is actually cosmic background radiation. It's basically just very low energy light that was emitted by the Big Bang. But anyway, so here at recombination, we can finally have neutral atoms, and simplest atom is hydrogen. So this is where most of our hydrogen was formed. You can also get some coincidental lucky reactions where 2 protons just happen to get close enough together and coalesce, and that forms a good bulk of the helium in our universe. And to a smaller extent, get a bit of lithium out of it as well. But that's basically all we can attribute to Big Bang fusion. So majority of our hydrogen, some majority of the helium, not all, and then maybe a little bit of lithium. And yeah, so that's where these very low mass elements come from. And so you can maybe imagine hydrogen and helium are 2 simplest elements, so they make up the majority of our universe even today. So in fact, astronomers like me consider anything heavier than helium to be a metal, including stuff like lithium or oxygen. Those are metals to me. The reason is that, well, even today, the vast majority of our universe is made up of hydrogen, so like 74%, and then a whole other quarter of our universe is made up of helium. And the rest of it is just a tiny percentage, almost too small to care about, right? So basically just say that we have hydrogen, helium, and some other stuff, which is our metals. Yeah. So how do we build up nuclei larger than hydrogen, helium? How do we build those metals? Well, as we said, like charges repel, same as a magnet, right? Push 2 north sides together, they're not going to like it. If you have a strong enough magnet, you might not even be able to force them together yourself. Similarly, opposite charges attract. So why is it allowed for us to force together protons and make bigger things? Well, the way that we do that is via fusion reactions. So fusion is different from fission. So fusion is pushing atoms or isotope or ions together to make bigger things. Fission is taking large nuclei and breaking them apart. So every current nuclear reactor that we have is a fission reactor. They take big atoms like uranium, sure, like over 100 protons in them, and they break them apart. Same with any atomic bomb. Those are all fission reactions, and they do release a lot of energy. But when you have really small atoms, like these are both hydrogen atoms. They just have different numbers of neutrons, so we call them different things. When you force together small atoms, that actually emits energy. So that would not happen if you were forcing together big atoms. It takes energy, as we'll see later in this talk, takes energy to fuse together big atoms, but get energy. It's actually more energetically favorable for these small atoms to coalesce. So that's very useful because, well, the only problem, of course, is that these like charges repel. So it's kind of hard to force them together. You have to get beyond this classical barrier. It's basically like charges repelling. So you need some environment that's very dense, so you have a high likelihood of things getting close enough to each other for the strong nuclear force to take over in here. And you also need somewhere that's really hot because you need these atoms or these ions to have a lot of energy, which allows them to, get close enough without being repelled very quickly. So what's the best place? Stars. So very center of stars. Yeah, question?
Yeah, the two questions. The helium ends up with 2 electrons, right?
Or, well, that's a neutral helium atom. We don't actually need to care about neutral atoms here. At the temperatures that most fusion reactions happen, you're not going to have any neutral atoms. It's all going to be ionized. That's because the electrons, they're about the ambient temperature of the center of the sun, which is 10 to the 7 Kelvin. It's about 300 Kelvin in this room right now. 10 to the 7, right? So you're not going to see basically any neutral atoms in the center of the sun or in any kind of fusion reactor.
There's just no electrons in this reaction.
Basically, they're just, they're in this plasma. Plasma is just a soup of ionized nuclei with their electrons free floating around, but it's your neutral atoms don't really factor into this at all.
So if you took the sun altogether, it's neutral?
Yes, correct. But basically none of those atoms, except for maybe some on the outside where it's cooler, even then it should be too hot on the photosphere to really get that many neutral atoms. So for the rest of this talk, there are no neutral atoms, basically, or you can think of it that way.
Is that considered the fourth ionization, the fourth state of matter?
Yeah, you could consider plasma as the fourth state of matter. If you go too deep, you get into many different states of matter that the condensed matter physicists in that building think about way more than I do. But those are usually under weird conditions that do not happen in these nice balls of plasma that I study. Any other questions?
Is that like as big as our sun, or?
That is our
That is our sun.
Well, that is.
yes.
No wonder it looks. Well, no wonder I was familiar with it.
Yeah, well, so you can start to image, right? Be hard to get this nice and this detailed of a picture of any other star. Closest one, is 4 light years away. So when you see it as like a little point source.
Hey, Natalie, going back to when you were talking about hydrogen during the Big Bang or before the Big Bang.
Yes.
What I remember several years ago is that before hydrogen, we really don't know how it came about. It assumes, or we have to assume that a hydrogen was there in the beginning, or do we have a theory that can describe how the hydrogen was formed before the Big Bang?
Yeah, so you're right. We can't really probe anything beyond this recombination epoch because we don't get light from anywhere before that recombination epoch. So you're correct. All we know is, basically what we can derive from first principles.
So hydrogen is the beginning point, not quarks.
quarks will definitely, like, there will be some period where quarks will have existed before hydrogen atoms, or at least in some part. I think it takes about, a microsecond for quarks to fuse into protons and neutrons.
So I guess another way to ask that is, what's the furthest we can go back?
Yeah.
At the Big Bang, let's say that's 0. But what's the furthest we can go after 0 based on theory and data?
Yeah,
A
so
few
data
seconds?
starts at recombination. We don't get anything except maybe neutrinos, but we haven't detected any neutrinos that we can confidently say are from before recombination. But everything else is theory. This isn't exactly what I study, so I can't say exactly, but I think our understanding starts probably around a microsecond, maybe a little bit earlier than that.
Microsecond after
Yes,
after 0.
after 0, correct.
Okay.
And yeah, that's based on, first principles. This isn't something we can observe.
So before the microsecond, you have no clue what that was. We have to assume it's quarks and things like that. because
Yeah,
I didn't
yeah.
know.
Yeah, something like that. Yeah.
Something like
Okay. Okay, so stars. So the center of stars is actually a fantastic place. It's very dense, very hot, and we are able to actually fuse together protons. In fact, what we consider a living star is one that fuses hydrogen into helium in its core. So before a star starts fusing hydrogen into helium, and after a star stops core fusing hydrogen, we consider it to no longer be a living star. Of course, it's not alive, but it's a good demarcation. And these stars form in beautiful nebulae. So all of these are star-forming nebula in our own galaxy. And basically what we want to do is we want to get from these big clouds of gas and dust. So again, this is all mostly hydrogen in here. There's some helium and then some very small percentage of metals. We want to get from these big things that span a few light years all the way down to the size of our sun, which is a lot smaller than this.
What does astronomer mean when he mentions dust?
Dust
Is it like the stuff I clean up from my bedroom floor?
honestly, kind of like the stuff you clean up is more molecules or like dead skin cells. Like people find that in there, but there are some molecules depending. But mostly it's hydrogen, some helium, and then some, just metals. Often there. Yeah, so anything heavier than helium. And you will find molecules in some of these places. Mostly H2, because hydrogen is the most common, so it's easy to form molecular hydrogen. But it's also easy to break up molecules. You only need basically just a photon or two, and photons are pretty ubiquitous, so it's also easy to break them apart. Anyway, what we want to do is we want to condense down these giant gas clouds into stars. And where that starts is with some small overdense regions in these clouds that, due to gravity, start falling in on themselves and start accreting the gas that surrounds them, basically. And what will happen, as you see, we start with some gas clouds. So this is, 200,000 times the size of the distance between our Earth to the sun. And start with some clumps. Each clump will start falling in on itself. This goes to like about 10,000 the size of the distance between our Earth and the sun. We call that an astronomical unit. And then this will start circularizing, forming protostars, and eventually it'll get down into something the size of our solar system, with maybe some little planets secreting in those rings around. And this, as you can maybe put up there, takes a long time. So if you call this T0, that's about 10 to 100,000 years. If you want to go to here, maybe more than 10 million years. But ultimately, what you end up with is a star. that is born onto what we call the main sequence. So the main sequence, which is this nice diagonal line, is where every star that we consider living, so again, core hydrogen fusing to be on. And they are born on this main sequence, and they live out most of their life on this main sequence before evolving off into these other things. And we have about 2 different evolutionary paths that stars take. So it can either be a small star like our sun and start again, as with all stars, from some nebula, form into a protostar, live life on the main sequence, and then evolve into a red giant, beyond into a white dwarf. Or we can take this massive star evolution path, which is for stars around maybe greater than 8 solar masses, all the way up to even 100 solar masses or more. And these guys, they're able to well, start from star forming nebula and then evolve into a main sequence star, live most of their life there. For massive stars, they live actually much shorter lives than their smaller counterparts. So the sun will live for maybe 10 billion years. It's already lived for about 4.6, so it's about halfway through its life. But massive stars are more like millions of years. So for a really massive star, it might only live 10 million years. Slightly less massive star, maybe 10 or 100 million years. That can be fairly short in astronomical time. And what these stars usually do is they form bigger red supergiants, and then they will explode at the end of their lives. And you will see how they come to explode and end up as these, well, everything kind of ends up as some kind of ultra compact remnant, but they have different paths and different end states. So anyway, let's start with a small mass star like our sun. So again, we form into a protostar, live most of our life as a main sequence. Our sun is G-type. So it's, you know, maybe sort of, it's actually a pretty good dividing line in terms of star masses. But anyway, for a typical G-type star, it'll live most of its life on the main sequence, and then eventually it will stop fusing hydrogen in its core. It will start fusing the hydrogen in its envelope. So any star needs to balance gravity with some kind of pressure that keeps it from imploding. Most stars on the main sequence, they'll do that by fusing hydrogen in their core, because hydrogen fusion produces a lot of energy, which also produces a lot of light, thankfully for us living here. But it also produces enough energy to stop implosion. Once hydrogen fusion can no longer happen, because the hydrogen has been used up in the core, it will then contract and start fusing the hydrogen in the outer shells of the star. So this is what happens as it evolves into a red giant. Eventually, the hydrogen in the shells will be used up, and it will ignite the helium in its core in a big bright flash. And after that, if it's big enough, might go down more paths of helium shell fusion, carbon fusion in the core, up to maybe oxygen. So we think our star will eventually fuse carbon and nitrogen into oxygen, and that's where it will stop. So after that, it can't get hot enough to fuse oxygen together. So at that point, it can no longer resist gravity, and the outer layers will blow off, and the inner core will condense down into this ultra compact remnant called a white dwarf, which we will talk a little bit about in a few slides. But in the process, yeah, so this is core fusion. So we start out on the main sequence with hydrogen core fusion, and then hydrogen shell burning, and then ignite helium, use helium, and if it's big enough, it'll fuse carbon into nitrogen and then oxygen. But ultimately, it will become a white dwarf. So this is a cluster of white dwarfs in our galaxy. and they just kind of sit there cooling off. They're fairly hot when they're born, but by the end, they just kind of sit there and cool. What's nicer is all that ejecta that gets launched off as the star compacts into the white dwarf. It launches a bunch of material out into the cosmos, creating these beautiful planetary nebula that have nothing at all to do with planets. They're just called that. And yeah, they're some of the greatest things to image, even with amateur telescopes. This is the Cat's Eye Nebula, a few different wavelengths, and you can see the nice white dwarf in the center. And any planetary nebula will have a white dwarf in the center. Might be too dim to see, but it will be there. Here's another example of planetary nebula. And the nice thing about these planetary nebula is that they actually spew a bunch of the outer layers of the star into the cosmos, allowing, well, it to eventually maybe be accreted into a nebula that starts forming stars, but that doesn't always happen, or doesn't usually happen with planetary nebula. But at the very least, they do enrich the universe somewhat. And as you can see, they produce carbon, nitrogen, which makes sense. I was produced in the core and the shells. Not as much oxygen, because that will stay locked up in the core if it's even produced at all. And then maybe some lithium. The other thing to note about this graph is these dying low mass stars also produce a bunch of larger elements. This is actually from another pathway. So as our sun moves off in sequence, it will go up and become a red giant. Then it will finally swing around to become a white dwarf here. But while it is a red giant, something else can happen in the outer layers. So basically, this process called the slow neutron capture nucleosynthesis can build up heavier elements. So the way that this works is that if you start with silver here, you add a neutron in, what will happen is something called a beta decay. So this is just some type of radioactive decay. It emits an electron or a positron. And in that beta decay, that neutron converts into a proton. And guess what? We have another proton. It's now cadmium. So that's essentially what the slow neutron capture process does, is it is slow because it waits for this beta decay, and that's how you can build up some of these bigger elements. And basically what we want to do is we want to stay in stable elements. So if we add a neutron, so this black line here is the so-called valley of stability. These are stable elements that will not radioactively decay. And if we start with some stable element here and we add a neutron, it's going to go into the blue beta decays. And what we want to do is we want to end up on a decay that puts us back in the valley of stability. That's the only way to get a stable nucleus out. Yeah.
Would you go back to the previous one?
Uh-huh.
Was this in the white dwarf?
No, so this is in the red giant star.
Oh, okay.
So this S process will happen in the outer layers of asymptotic giant branch stars. Yes.
It seems like neutrons and protons can
Yes.
change.
Yes.
Neutron stars.
Yes.
They're like
Yeah. So they're
charged.
yeah. It's dependent on what quarks are making up the neutron, but it's some particle physics process that allows them in some circumstances to change through radioactive decay.
And you, the very first, the proto star, how do they come together? By gravity?
Gravity.
But they're electric. What about their ions? So does that play any part into it?
Gravity is there's a lot of mass here.
Okay.
There's a lot more mass than is required to actually pull things together in spite of electric repulsion. Question.
In that earlier, so that one. So when the silver becomes cadmium, did you say that a neutron becomes a proton?
Correct. So a neutron added here will beta decay, release an electron or a positron, and it will become a proton. Yes.
That's pretty cool.
Yes.
So within our star, carbon and oxygen are made within the star?
Not currently. Right now, our star is on the main sequence. It is only fusing hydrogen into helium in its core. It is made of other metals, but those are from when it was formed.
But within some stars, it could be made.
Within
Bigger
post
stars?
main sequence stars, yes.
Pardon?
Within post main sequence stars. So as they turn into red giants, stars like our sun can begin to fuse heavier elements than hydrogen. Question.
So for the silver in the previous slide,
Mhm.
that's just an example of how those two processes can increase the atomic number.
Correct.
Okay, so would certain isotopes of carbon and oxygen create that kind of process in the red supergiants or the giants?
So this is mostly for heavier things. I mean, you have to build up to here too, so I assume it happens in some capacity. But usually when you talk about S process, you're talking about these heavier elements. Other questions? Yeah, so this S process allows us to build up very heavy elements. In fact, right, so most of the lead in our universe was created in these asymptotic giant branch stars, these post main sequence low mass stars, and you can see other, significant amounts of mercury, strontium, etc. All have, we think, someplace or in some capacity made in these red giant branch stars. Okay, well, what about these white dwarfs? So we see that white dwarfs can also make some elements. How does that work? Well, white dwarfs, as I said, are held up by electron degeneracy pressure. So they are very compact things where effectively what you're doing is you're overfilling each individual atom with electrons. So if you remember from a chemistry class that the Pauli exclusion principle only allows for 2 electrons to exist per orbital in an atom, you know that if you try to cram more electrons into a nucleus, that isn't going to work very well. There's this repulsion just from the quantum mechanical nature of these atoms that doesn't allow you to cram more than 2 electrons per energy state. So this electron pressure is actually very effective at keeping these white dwarfs from imploding. However, that only works up into a point. So if you, so for example, if we have a white dwarf in a binary system, so this is Sirius A and B, so these 2 stars are orbiting each other. You have this kind of a binary system of either 2 white dwarfs orbiting each other or a white dwarf orbiting another star. What can happen is a couple of things. So either you have 2 white dwarfs, they can in-spiral and collide with each other, or you can have a white dwarf that accretes a bunch of mass from another star. And what happens is that if you get over a certain mass threshold, so we say it's about 1.4 solar masses, white dwarfs are normally less than a solar mass, maybe up to this limit of 1.4 solar masses. What happens if you go over is an explosion. So that electron degeneracy pressure no longer helps you keep the star bound, and you get this really bright explosion called a type 1a supernova. So type 1a supernova are really cool. They are very, very bright, and we think we understand the physics of them very well. So we understand basically if we observe a 1a supernova with a certain brightness, we think we understand how far away it is. They're called standard candles, which allow us to basically measure distances on this cosmic distance ladder. So, you can start out pretty short with something like radar to measure distance to close things to us. And then you can go through these other types of distance measurements. But 1A supernovae are really nice because they are so bright that they actually outshine their galaxies. So we can see them from very, very, very far away. Here's a nice picture of this 1A that exploded in the Pinwheel Galaxy, which you may have heard of if you've been paying attention to astronomy news this year. I'll get to that later in this presentation, but as you can see, this 1A outshines its entire galaxy. It looks just as bright as any of these foreground stars in our galaxy. So they're very nice, very bright, and for the most part, fairly consistent explosions, so we can use them to determine distances to other galaxies.
Can you go back one more? Yeah, that Hubble's law, well, that looks even further than Type 1A supernovae.
Yeah, so this is the thing that we kind of want to calibrate using all of these things.
But that's kind of indirect. Hubble's not,
Yeah.
not,
Exactly.
all the others are direct.
Yeah,
Hubble's based on a theory.
yeah. And we're trying to calculate the Hubble constant using observed things
Right.
so that we
That
can
keeps
actually.
changing every few weeks. I mean. it
I mean,
gets
there's some
better and better,
controversy.
right? The Hubble constant more accurate.
Yeah, well, there's like two camps and their error bars aren't exactly overlapping very well,
Oh.
but that's an active area of research. Yes.
How are planetary nebulae used for is the calculation? Are they also standard paranormal?
So planetary nebula, like the nebula itself is diffuse gas. So we can't see that from very far away. We can only really see planetary nebula that are in our own galaxy. So it's not the planetary nebula that's used, it's the explosion that happens if the white dwarf at the center of the planetary nebula explodes. Question.
Is it type 1A, is it the fact that it explodes and then it explodes again that you use to figure out that it's a 1A?
So we think it's only one explosion. Correct me if I'm wrong, but
It's that characteristic?
yeah,
hump?
it should only be one hump.
Okay,
So we identify 1As mostly by their spectra. So spreading out their light into a rainbow and see where there are like absorption or emission features. That'll tell you if it's a 1A or not. Versus another type of supernova, because all the light curves are basically the same.
How long does a type 1A supernova last?
So most supernovae, unless they're very, very close, they'll fade over like a month's time scale about. If it's close, you might be able to see emission from the nebula for a lot longer. But yeah, month's time scale for supernova, any type of supernova. Okay.
What's happening within the white dwarf that allows us to see it?
Well, it's hot. It's hot and it emits thermally, just like all of us do.
So it's just radiating?
Yeah, it's actually fairly hot, right? If we look at the mean sequence, the surface temperature of white dwarfs, it's 20,000 Kelvin. It's hotter than our own star, which is like.
But there's no
6,000.
nuclear fusion going.
No nuclear fusion at all. It is solely composed of electrons. And
Just cooling in the timbers.
Yep. And, ultimately we think that these will cool to black dwarfs, which, are just balls of electrons that aren't even hot anymore. So they don't emit anything. Other questions? Okay. So yeah, type 1A supernovae. And we see that these exploding white dwarfs produce a lot of these sort of low mass heavy elements, especially stuff like iron. So the majority of the iron in our universe come from white dwarf explosions. Okay, so let's go down the other evolutionary track, talk about massive stars. So massive stars start their lives, the nebula, form a protostar, live as a main sequence star, again, for less time than smaller stars, but what's more interesting is that they are actually hot enough in their core once they evolve off the main sequence to continue fusing beyond oxygen. So what massive stars will do as they die effectively is they will start fusing heavier and heavier elements in their core, all the way up to iron. So everything left of iron, when you push the nuclei together, you get energy out. anything to the right of iron, including iron, if you put the nuclei together, it requires energy to get the nuclei to fuse. So that means that, well, star gets up here, you know, it's fine using hydrogen, it's a little less fine using helium, produces less energy, right? A lot less energy using helium than iron. Using carbon, will extract some energy, oxygen, all the way up to just before iron. But when it starts to fuse iron, oh no, star can't produce energy. That means that there's no pressure support against gravity. So once a star is at the point where it needs to fuse iron to create energy, it can't, and it starts collapsing. So yeah, basically what happens is this core will become ultra dense. The outer layers will also start infalling because of gravity, but in the very center, right, there's some shells of hydrogen and other lighter elements around here. They will infall, and as they infall and get more dense, they will start fusing, creating a bunch of energy that explodes outward and hits all of this outer layers and eventually unbinds the star, mostly due to these neutrinos that are produced by the fusion reaction, but I won't get too much into that. In any case, what we end up with is a core collapse supernova. So this is again the Pinwheel Galaxy, now taken earlier this year, of this supernova that is a core collapse supernova caused by a massive star that has basically tried to fuse hydrogen and, fuse iron and failed, and exploded out as this, again, giant galaxy outshining supernova. So it's very cool. This galaxy is, you know, like 6 megaparsecs from us. It's very, very close.
When did that happen?
This happened in March. Was it March?
May.
May. He studies the supernova. Yeah.
Are there two? There's one up in the left and there's one down on the right. Are there two of them?
No, he's talking about this star.
No, down.
Where? Oh,
It's blinking. Keep going down. It's blinking.
like this one? Oh, yeah. So
No, yeah.
that's just effect.
Effect. Oh,
Yeah.
effect of both.
This, you know, 2 images being compared, they have different light distribution or different probably integration times or something like that. But the point is, right, there's nothing behind there, right? And then there's something. So that is what we call a type 2 supernova, or more generally a core collapse supernova. There are other types of core collapse supernova, but this one is specifically a type 2. And yeah, this is really cool. We only get a supernova this close maybe once a decade. So really exciting time for people like me or Sergey who are in the transient field. And yeah, it's really cool to get this bright of an object this close. Here's another picture of core collapse supernova. So you start with maybe this is the progenitor star that we can actually see, and then it blew up. This star, if I remember correctly, was in the Large Magellanic Cloud, so even closer than the other supernova. So you can actually see something about the progenitor star, and then big and bright outshines the rest of the stars there. Yeah, and what happens is you get an ultra compact remnant at the center. This time, either if you're a low mass massive star, you end up with what's called a neutron star, which is just, again, a ball of degenerate neutrons this time. Or you could form a black hole if there's enough gas. And meanwhile, the outer layers pop up into these beautiful nebulae. So this is the Crab Nebula, and I forget what this one is called, but beautiful things. This one has a neutron star in the center of it. I've heard of the Crab pulsar. This one has a black hole in the center. Yes.
The neutrons came from photons.
The neutrons just kind of coalesce at the center. Some of them probably came from protons. Yes.
Wasn't the Crab Nebula observed to be created by this planet?
Yeah, so the supernova that created the Crab Nebula was observed by ancient Chinese and other ancient astronomers. So it's really cool to be able to go back in historical records and be able to point to this thing on the sky that you can point your telescope to today and see the remnant that exploded a few hundred years ago. Yes.
You talked about supernovae that are closer to us.
Mhm.
We have to worry about a supernova that's so close to us that it can actually burn us, or is that a possibility?
I mean, theoretically, if it was close enough, closest star to us is about 4 light years. But it's not going to happen in our lifetimes. The next one that could go off is Betelgeuse, but it's not going to go off in our lifetimes, most likely.
So what's the physics of the degeneration? Since
That's a good
Pauling said it can't happen
question.
and you're saying it does.
So, well, enough gravity will pull it together. So Pauli is for specifically electrons. There's a different process for neutrons, and we don't totally understand that. We don't really understand the equation of state for a neutron star yet. But basically, there's nothing that is being violated in a white dwarf. So a ball of degenerate electrons. It's just held up by degeneracy pressure because of the Pauli-Solution principle, because you can't force a certain number of electrons into a physical space.
So determine the size of the white dwarf. Basically.
Size, yeah, mostly. Anyway, other questions? So more pretty pictures of core collapse, supernova, nebula, and as you can see, these exploding massive stars also create a lot of these lower mass elements. So a lot of reasonable magnesium and sodium created in core collapse supernovae and ejected into the outer cosmos via the nebula, basically. Yes.
Are we looking at all the different types of being? What is this the whole like the
This is the entire periodic table, if that's what you're asking.
like in chemistry?
Yes. These are all the individual elements
Yes,
that exist in our world.
elements.
There are, some that are created in labs
Not where they
that,
came from.
that won't be created in the natural world. They have to be man-made.
That's pretty remarkable that they all fit together.
Oh, yeah. This is very cool. Question.
What is special about iron, such that the star cannot produce energy? What's the profile that's making that happen?
It's atomic physics, basically. Essentially, you cannot force that many electrons, and that many protons together without requiring energy input. If I was an atomic physicist, I could even tell you more about that, but I am not. Other questions? Yes.
A long time ago, the astronomy would say that all of the heavy elements were produced by supernova. Is that the change that you say
Yes,
has occurred in the last
exactly.
10 years?
Yes.
Okay.
And we're just about getting to the reason why.
Okay.
Other questions? Okay, so on that note, these massive stars, after they supernova, they leave these remnants, neutron stars and black holes. Again, these are ultra compact objects. And what can happen is, where am I? Here we go. So, yeah, if you end up having two massive stars in a binary system, which is actually favored, so most massive stars we think form and live their lives in binary or even trinary systems, you can end up with two massive stars that have evolved, supernovaed, and are now two ultra compact neutron stars orbiting each other. And eventually that orbit will decay and you get a neutron star collision. This is even more energetic than a supernova. It's very cool. It creates what's called a gamma ray burst, which is some of the brightest light and most high energy light ever seen anywhere in our universe. That'll come out the poles of this neutron star collision. And in that neutron star collision, we get these really neutron rich outflows that accrete around the newly formed black hole. And this happens, okay, well, the gamma ray burst here, and this is actually the detected gravitational wave emission from the collision of those two massive neutron stars. This was detected for the first time in 2017. It's the only detected neutron star collision in by LIGO, by Gravitational Wave Observatory, and it's revolutionized the field of both nucleosynthesis and some parts of transient astronomy. It's very cool. LIGO is actually running again right now, and we're trying to find more of these, and it's not going as well as it did back when we detected this one, but this is a special event. Question?
All right, well, but you were talking earlier about there's a limit of where you can see light to like 300,000 years or 280,000 years. I can't remember what it was.
Oh, yeah, from the Big
But
Bang.
gravitational waves don't have that limit. So is that something that is coming into play? Yeah, or maybe it's too early in the
Yeah,
lifetime.
we're not at that sensitivity.
Yeah.
LIGO can maybe see like 200 megaparsecs away, which all in all is like just barely what we need for transient science. Maybe even only 100 megaparsecs by itself. Yeah, so.
But it's fairly new, so something that
Yeah.
could occur in the future. Like,
Right now, gravitational wave science is more focused on either the big events, so like LIGO observes a lot of binary black hole mergers, like binary supermassive black hole mergers at the center of galaxies. It'll detect some neutron star black hole and neutron star collisions. But there are actually new instruments coming online that aim to detect like white dwarf collisions or other smaller compact object mergers. There are things that we do use pulsar timing arrays to detect some other background, I think, gravitational wave emission, but this is a brand new field. You know, it's really cool to be a part of.
What is a gravitational wave, and what would happen if it would we all of a sudden get heavier or lighter? If,
Barely. So gravitational wave is essentially a wave in the fabric of space-time. Sounds weird, but it actually works. Basically, massive things, including all of us, affect our, have gravity of our own. And as we move through space, our gravity affects space-time, or effectively the fabric of the universe, and causes oscillations. Oscillations from even supermassive black holes that collide are very, very, very minute. Like the big thing that LIGO has to do is be giant and very precise with its measurements and error analysis, so it can actually, extract these signals from noise in the detectors. So it's very minute, but it is there, and it does cause effects that we can actually see. Question?
Does LIGO use like a really long laser?
Yes.
Detector with like.
Yes.
Okay.
LIGO stands for LI, so Laser Interferometry Gravitational Observatory, something like that. Yeah, it's very cool.
A massive surge of energy would cause a gravitational wave.
Yeah. It's more about the mass, but mass can be converted to energy and vice versa. So usually things that interact gravitationally are very massive things. Yeah.
I just make the point, all the gravitational waves that LIGO has detected have passed through us.
Yeah.
And, so It would have to be.
but it's very subtle. Like
Yeah.
it barely affects,
Yeah.
very precisely monitored light in a giant chamber. So, it's nothing that really affects our daily lives, but it is there, and it's really cool to measure and figure out the implications of physically. Anyway, one question, yeah.
Only you said this already. What is the typical difference between the signature in the gravitational wave and the Fermi state?
So this is just saying that it's correlated. So we saw this neutron star merger in 2017 in both gamma rays and optical light, visible light, as well as by LIGO and gravitational waves. So this was a really, really cool event because we got to combine multi-messenger modes of observation to, see this really cool high energy explosion far, far away. Okay, so in case, neutron star mergers are very cool for a lot of reasons, but one of the reasons I think they're very cool is because they're very neutron rich, hence neutron stars. And okay, this is a picture of the explosion in 2017 in visible light, taken by Hubble, actually. You can see it change over time a bit. But anyway, these neutron stars allow for something called rapid neutron capture nucleosynthesis, which is like the S process, but instead of waiting for the beta decay, you just get a ton of neutrons bombarding a heavy nucleus, and that basically it'll decay, but in that decay, you get a new heavier element. And this R process is what allows you to create basically anything heavier than about gold. So if you have a gold ring on or gold jewelry, that the atoms that make up that jewelry were most likely made in a neutron star merger. Yeah, so very cool. That also includes, almost all silver. If you've ever played with like new magnets, that's all created in a neutron star collision. And then, spew it out into the cosmos, till it creates new stars and eventually our solar system.
So how much gold would be created in some explosion?
Very little compared to the entire.
We have lots of gold right here, so there must have been billions of these explosions.
More like the stars that create them are very massive. So in terms of an astronomical scale, there's very little metals created, including everything down here. But there's a lot of mass and a lot of hydrogen in those stars, or there was a lot of hydrogen when those stars were created. So you end up with, an Earth's amount of gold or something like that. Yes.
Okay, so then those elements just kind of swirl around in space until they create planets?
Yep, until they find themselves in a really dense region of a star-forming nebula and coalesce into a new solar system.
So you talked about a gold ring or a gold coin. It's a lot of gold atoms that happen to find each other. How do they find each other and hang on to each other?
I mean, first order, it's gravity. Second order, it's chemistry. I don't really do chemistry, but bunch of physics goes into how a protostar will form and the protoplanetary disk around that star, and some point it becomes earth science and geology, why it gets found in certain locations in our planet. Anyway, so this is our current picture. This is mostly agreed upon by any astronomer you're going to talk to. There are other places where these R process elements may also be formed. So part of my research is looking at these type of supernovae. So this is called a 1C supernova with broad lines. They have similar physics, so they get to similar energies. They have a black hole at the center once they supernova, and some kind of similar accretion disk to what forms in a neutron star collision. So it is theorized that our process may also occur in these types of supernovae. My research is trying to figure out whether that is true observationally. We don't think that a lot of our process elements are going to be created in these explosions, but there might be some. And in any case, it's interesting to understand, where elements come from and how much these supernovae may contribute to the chemical evolution of especially those really heavy elements. So yeah, this is the picture that we have today. And I think that's about it. What was I going to say?
So,
yeah.
On your
Yes.
chart of the elements, you didn't, beryllium and boron are
Yes.
pretty low mass elements,
Yeah,
yet they're not created in stars.
correct, mostly.
Your thing seems to say.
Yeah, the interesting thing about these low mass elements, so like some part of lithium, most of beryllium and boron, is that these elements, if we go back here, are not they don't release much energy compared to their the elements around them. So they aren't really favored when you fuse stars. In fact, beryllium is the isotope of beryllium that gets formed in stars is radioactive and decays very fast. So you don't get much beryllium out of even like a low mass star or even a high mass star in just normal fusion after the main sequence. But what does happen is it's called cosmic ray fission. So if you take a big nucleus and you shoot it with some kind of highly charged particle, which we call a cosmic ray. There are different types of cosmic rays. They're just fast particles. They could be random protons or electrons or other types of particles, maybe even a helium nucleus. But if you shoot one of these at a big nucleus, fission can happen. So again, fission is breaking things apart. And that's what happens. And that creates most of the lithium, well, maybe not most of the lithium, but most of the beryllium in our universe, which then can decay into boron. And if you remember from the very beginning, there was barely any beryllium and boron, even in our sun or in the wider universe. So this is a much smaller effect than anything else in here. Okay, I think that.
So are those pretty rare elements then?
Yeah, fairly rare, at least on a cosmic terms. I don't know Earth chemistry that well, but in terms of the universe, yes, they're fairly rare. Okay, and that is basically my talk. With all astronomy talks, I feel like you have to end with a pretty nebula, the planetary nebula. But I'm happy to take any questions.